The Universe in a Nutshell by Stephen Hawking. Picture this: you're holding the entire universe in your hand. Not some miniature model or artistic representation, but literally everything. Every star burning billions of miles away, every galaxy spiraling through the void, every moment that ever was and ever could be, all nestled inside something as small as a walnut shell. Sounds like fantasy, right? Actually, it's Shakespeare. Hamlet said he could be, quote, bounded in a nutshell and count myself a king of infinite space. Pretty poetic. But here's where it gets wild. What if one of history's greatest scientific minds told you this isn't just beautiful poetry, but actually the most accurate way to describe reality? That's exactly what Stephen Hawking did. You know the image. The brilliant physicist in a wheelchair, his body held captive by illness, while his mind roamed freely across the cosmos, speaking to millions through that iconic computer-generated voice. His first blockbuster book, A Brief History of Time, wasn't just a bestseller. It was a cultural phenomenon, selling millions of copies and camping out on the bestseller list for over 4 years. He took the most mind-bending concepts in physics and made them accessible to everyone. But Hawking wasn't done. Science kept moving forward, and so did his thinking. That's why he gave us The Universe in a Nutshell. This isn't just part 2. It's deeper, stranger, and more wonderful. This is about the fundamental nature of reality itself. Over 10 million copies flew off the shelves in its first decade. Proof that we're a species desperate to understand where we fit in the grand cosmic picture. Today we're going to see the universe through Stephen Hawking's eyes. We're diving into a reality where time bends like rubber, where the universe doesn't have just one history but every possible history, and where everything you see might actually be a hologram projected from the edge of space itself. Here's what I promise you. By the time we're done, these ideas won't just make sense intellectually, you'll feel them in your bones. The next time you look up at the night sky, you won't see distant dots of light. You'll see an unfolding story, and you'll know that you're part of it. So take a breath. Let go of everything you think you know. We're about to crack open the nutshell. Our story doesn't start among the stars. It starts in a Swiss patent office in the early 1900s. A young guy named Albert Einstein, who wasn't some child prodigy and couldn't even land a university job, was quietly launching 2 revolutions that would shatter everything we thought we knew about time, space, and reality. Back then, scientists were pretty cocky. They thought they were close to figuring everything out. They believed space was filled with this invisible stuff called ether, and light was just a wave traveling through it, like sound waves moving through air. Nice and tidy, right? Except there was a problem. When you're on a moving train and throw a ball forward, its speed is your throw plus the train's speed. Basic physics. Scientists figured the same thing should work for light. Since Earth is moving through this ether, light should appear faster or slower depending on which direction we're looking. But when they actually tested this in the famous Michelson-Morley experiment, they found something completely bonkers. Light always traveled at exactly the same speed. Always. No matter how fast you were moving or which direction you were going, light never changed. It was like the universe had a cosmic speed limit that nothing could break, and somehow it was the same for everyone, everywhere. Enter Einstein. In 1905, this patent clerk published a paper that took this weird observation and built an entirely new reality from it. His radical idea was simple. What if there is no ether? What if the laws of physics, including light's speed, are identical for everyone, regardless of how they're moving? The consequences were mind-blowing. For this to work, Einstein realized we had to give up something we all take completely for granted, the idea that time is the same for everyone. He proposed that time is relative. Everyone has their own personal clock. If you and I are sitting together having coffee, our clocks tick at the same rate. But if you hop in a spaceship and zoom near light speed, your clock will tick more slowly than mine. This isn't science fiction, it's proven fact. Scientists have flown atomic clocks on airplanes around the world. And when they land, those clocks are slightly out of sync with identical clocks that stayed on the ground. Time itself stretches and contracts depending on how you're moving. This was special relativity, and it came with another bombshell. Einstein showed that as you pump energy into speeding something up, its mass actually increases, it gets heavier. To accelerate anything to light speed would take infinite energy, which is why nothing can break that cosmic speed limit. This led to the most famous equation ever written, E equals mc squared. Mass and energy are interchangeable. A tiny bit of mass can convert into enormous energy. This is why the sun shines. It's also, tragically, why atomic bombs work. Einstein, who was a lifelong pacifist, was horrified when his discovery became a weapon. He once said, "Politics is for the moment, but an equation is for eternity." His relativity equations are his true legacy. But Einstein wasn't finished. His relativity theory meshed beautifully with electricity and magnetism, but it crashed headlong into Isaac Newton's law of gravity. Newton said gravity was instantaneous. If the sun vanished right now, we'd immediately feel the gravitational change here on Earth. But Einstein had just proven that nothing, not even information, can travel faster than light. It takes 8 minutes for sunlight to reach us, so how could gravity be instant? This puzzle gnawed at Einstein for years. The breakthrough came when he had what he called his happiest thought. He realized that acceleration and gravity are deeply connected. Imagine you're in a closed elevator with no windows. Your feet press against the floor. Can you tell if you're on Earth, held down by gravity, or in a rocket ship in deep space, accelerating upward? You can't. The feeling is identical. From this simple insight, Einstein made a gigantic leap. Gravity isn't actually a force, it's the shape of space and time. Mass and energy warp the fabric of space-time itself, like a bowling ball creating a dip in a rubber sheet. Smaller objects rolling nearby aren't pulled by the bowling ball. They're just following the curves in the sheet. That's what planets do. They aren't being yanked by the sun. They're following the straightest possible path through a space-time that's been curved by the sun's enormous mass. This new theory was general relativity. Space and time went from being a static stage to active players in the cosmic drama. This theory made a bold prediction. If mass curves space-time, then even light should bend when passing a massive object like the sun. In 1919, during a solar eclipse, astronomers watched the light from distant stars passing near the sun. The light bent, exactly as Einstein's equations predicted. It was a stunning vindication. Einstein became an overnight global celebrity, and our understanding of the universe was forever transformed. But general relativity revealed something even bigger. When Einstein examined his own equations, he found they didn't allow for a static, unchanging universe. They demanded that the universe must be either expanding or contracting. Everyone at the time believed the universe was eternal and unchanging, so Einstein thought he'd screwed up. He even added a mathematical fudge factor, the cosmological constant, to force his equations to produce a static universe. He later called this the biggest blunder of his life. Because in the 1920s, astronomer Edwin Hubble made a landmark discovery. He observed that distant galaxies were all moving away from us. The farther away they were, the faster they were receding. The universe was expanding. This was the final puzzle piece. If the universe is expanding now, then, in the past, everything must have been closer together. Rewind the cosmic clock about 15 billion years, and everything in the entire universe, every star, every galaxy, all matter and energy, would have been crushed into an unimaginably hot, dense point. This was the beginning, the Big Bang. Stephen Hawking, working with colleague Roger Penrose, took Einstein's general relativity and proved that if the theory was correct, the universe must have had a beginning. Not maybe, must have. The theory that bent space and time also gave time itself a starting gun. But this created a profound problem. At the Big Bang moment, density and temperature would have been infinite. This is what physicists call a singularity. At a singularity, all the laws of physics, including Einstein's theory, completely break down. General relativity could tell us there was a beginning, but it couldn't tell us how it began, or what caused it. What happened before the Big Bang? For a long time, this was considered territory for philosophers and theologians, not scientists. But Hawking wasn't satisfied with that. If the laws of physics fail at the beginning, what stops them from failing at other times? A law that only sometimes works isn't really a law at all. The reason general relativity breaks down, Hawking explained, is that it's incomplete. It's a classical theory, describing the large-scale universe beautifully. But it doesn't include the other great revolution of 20th century physics, quantum mechanics. Quantum mechanics is the science of the incredibly small atoms and the particles inside them. At that scale, reality gets fuzzy and weird. It's governed by the uncertainty principle, which says you can't simultaneously know both a particle's exact position and its exact speed. The more precisely you measure one, the fuzzier the other becomes. This fundamental randomness troubled Einstein deeply. He famously said, "God does not play dice." But, as Hawking liked to joke, all the evidence suggests God is quite the gambler. The quantum world deals in probabilities, not certainties, and it has a strange property. Even in what we think of as empty space, a perfect vacuum, things are constantly happening. The uncertainty principle means that empty space is actually seething with energy. Pairs of virtual particles constantly pop into existence, fly apart, then come back together to annihilate each other. They exist for such fleeting moments we can't directly see them, but their effects are real and measurable. The vacuum isn't empty at all. This is crucial. Near the Big Bang, the universe was incredibly small, and these quantum effects would have dominated everything. To understand the universe's origin, we need a theory that marries the two pillars of modern physics: Einstein's general relativity for the very large, and quantum mechanics for the very small. We need a quantum theory of gravity. For decades, this has been physics' holy grail. The search has led to some truly mind-bending ideas. One early attempt was supergravity theory, which proposed a new kind of symmetry in the universe called supersymmetry. The idea is that every particle we know has a superpartner particle. These superpartners help cancel out some troubling infinities that crop up when trying to combine gravity and quantum mechanics. Then, in the 1980s, a revolutionary idea swept through physics: string theory. String theory says the fundamental building blocks of reality aren't point-like particles, but tiny, vibrating, one-dimensional strings. Just like a violin string vibrates at different frequencies to produce different notes, these fundamental strings vibrate in different patterns. One vibration pattern appears to us as an electron, another as a photon, another as a quark. All the particles and forces of nature are just different notes played by these tiny strings. String theory was incredibly elegant, and for a while it seemed like the theory of everything, but it had problems. There wasn't just one string theory, there were 5. And they only worked if the universe had 10 dimensions, our familiar 3 space dimensions, and 1 time dimension, plus 6 other dimensions curled up so small we can't see them. It was confusing. But then, in the 1990s, physicists discovered unexpected connections, or dualities, between the 5 string theories and supergravity. They realized these weren't different theories at all. They were different facets of a single, deeper underlying theory that exists in 11 dimensions. This mysterious parent theory got a name, M theory. The M supposedly stands for magic, mystery, or membrane, depending on who you ask. Because in M theory, strings aren't the only fundamental objects. There are also higher dimensional objects called p-branes. A 1 brane is a string. A 2 brane is a surface, like a membrane. M theory allows for branes of many dimensions. We don't have the complete picture of M theory yet. It's like a jigsaw puzzle, where we've only figured out the border pieces. The middle is still mysterious. But this quest for a unified theory has opened entirely new ways of thinking about the universe and the beginning of time itself. This brings us back to the Big Bang problem. How can we describe a beginning without a boundary, a starting point, where physics doesn't collapse? Here, Hawking, working with physicist Jim Hartle, introduced one of his most profound ideas, the no-boundary proposal. To understand it, we need a strange but powerful concept, imaginary time. Don't let the name intimidate you. It's a well-defined mathematical idea. Think of ordinary time as a horizontal line stretching from past to future. Imaginary time is simply another line running perpendicular to real time, like vertical to horizontal. In Einstein's classical theory, real time is special. You can only move forward in it. But in quantum gravity mathematics, imaginary time behaves just like another space dimension. You can move back and forth in it, just like moving left or right. The no-boundary proposal suggests that the universe's history in imaginary time has no boundary, no beginning or end. It's a closed surface, like Earth's surface. You can travel anywhere on Earth, but you'll never fall off an edge or find a starting point. The South Pole is a point on Earth, but you can't go further south than the South Pole. It's a beginning that isn't a jagged edge or a singularity. It's a smooth, regular point. If the universe's history in imaginary time is this smooth, closed surface, then our history in real time emerges from it. The Big Bang isn't a moment where physics broke down. It's the moment corresponding to the South Pole of the universe's imaginary time history. It's the beginning of real time, but it emerges from a timeless, boundaryless state. In this picture, the universe is completely self-contained. It doesn't need anything outside itself to light the fuse and get things started. The universe, and time itself, simply is. It's brought into existence by the laws of physics themselves. But this raises another puzzle. If the universe can have a history, why this particular history? Why a universe with stars and galaxies and us? This is where another fascinating idea comes in, first developed by physicist Richard Feynman. Feynman revolutionized quantum mechanics with his multiple histories, or sum over histories idea. He said that to get from point A to point B, a particle doesn't take just one path. It takes every single possible path, all at once. It travels in a straight line. It zigzags wildly. It goes out to the edge of the galaxy and back. Each of these histories has a certain probability. When you add up all the probabilities of all possible paths, you get the final outcome we actually observe. For large objects like a baseball, all the weird paths cancel out, leaving only the classical path Newton described. But for a tiny particle, this multiplicity of histories is real. Hawking proposed applying this same idea to the entire universe. The universe doesn't have a single history. It has every possible history, each with its own probability. There's a history where the universe expanded, then immediately collapsed. There's a history where it's cold and empty. There's even a history, Hawking joked, where Belize won every Olympic gold medal, though its probability is vanishingly small. We live in one of these histories. So what singles it out? This is where we encounter the anthropic principle. Simply put, the anthropic principle says the universe must be the way it is, because if it were different, we wouldn't be here to observe it. Many possible universe histories aren't suitable for intelligent life. Some last only fractions of a second. Some are so curved that stars and planets could never form. Some are just empty. The very fact that we exist, asking these questions, means we must inhabit one of the minority of histories that allows galaxies, stars, and ultimately life to form. For example, why does space have 3 dimensions? In M-theory, it could have many more. The anthropic principle offers an explanation. In a 2-dimensional universe, a creature with a digestive tract going all the way through would fall into 2 pieces. Hard to imagine complex life evolving. In a universe with 4 or more large space dimensions, gravity would work differently. Planetary orbits around stars would be unstable. Planets would spiral into their sun or fly off into cold darkness. Atoms themselves might not be stable. So it seems only a universe with 3 large space dimensions is stable enough for beings like us to evolve. The universe is the way it is, because it's the only kind of universe that can produce observers to wonder about it. This brings us back to Shakespeare's line, "The universe in a nutshell." Hawking suggests that the most probable history for a universe containing intelligent life is one that begins from a tiny, slightly flattened sphere in imaginary time. This small, closed, boundaryless nutshell contains all the information, every law, every particle, every possibility that unfolds into the vast, expanding, 14-billion-year-old cosmos we see around us. We could indeed be bounded in a nutshell and count ourselves kings of infinite space. This new understanding opens up even stranger possibilities. If space-time can be warped so dramatically, could we travel through it? Could we travel in time? Time travel is usually science fiction territory, but general relativity does seem to permit it, at least theoretically. Space-time could be warped so severely that it creates wormholes, tunnels, or shortcuts through space and time. You could enter one end of a wormhole and emerge on the other side of the galaxy, or even at an earlier time. This naturally leads to famous paradoxes. The grandfather paradox asks, what if you went back in time and prevented your grandparents from meeting? You'd never be born, but if you were never born, you couldn't have gone back to stop them from meeting. It's a logical contradiction. Hawking was fascinated by this problem. He asked, do the laws of physics protect history from being changed? He proposed what he called the chronology protection conjecture. He argued that physics conspires to prevent time travel on a large scale. His reasoning was based on quantum mechanics. To create a wormhole and keep it open long enough for a spaceship to pass through would require matter with negative energy density. As we've seen, quantum fluctuations can create negative energy locally, but Hawking's calculations suggested that as you try to build a time machine, the virtual particles circulating through the wormhole would build up to infinite energy density right at the entrance. Anyone or anything trying to enter would be destroyed by a bolt of radiation. History, it seems, protects itself from paradoxes. While large-scale time travel might be impossible, Hawking's work on black holes introduced another paradox that threatened the very predictability of the universe. Black holes are regions of space-time warped so severely that nothing, not even light, can escape. But in 1974, Hawking made his most famous discovery. By combining general relativity with quantum mechanics, he showed that black holes aren't completely black. They radiate. Because of quantum fluctuations, pairs of virtual particles constantly pop into existence near the event horizon, the black hole's point of no return. Occasionally, one particle of a pair falls into the black hole while the other escapes. To a distant observer, it looks like the black hole emitted a particle. This steady stream of particles is now called Hawking radiation. This radiation carries energy away from the black hole, meaning the black hole loses mass. Over an immense time period, it will shrink and eventually evaporate completely, disappearing in a final burst of radiation. This created a deep puzzle, the information loss paradox. When something falls into a black hole, a book, a spaceship, an astronaut, all the information that made it unique seems trapped inside. The no-hair theorem says a black hole is defined only by its mass, charge, and spin. It has no hair, no other features. So what happens to all the information about what fell in when the black hole evaporates? Does it disappear from the universe forever? If it does, it violates a fundamental principle of quantum mechanics, which says information can never truly be lost. This would mean the universe isn't deterministic. Even knowing the complete state of the universe at one moment, we couldn't predict the future with certainty, because information could randomly vanish down black holes. Our ability to make definite predictions would collapse to zero. This debate raged for decades, with Hawking himself arguing for a long time that information was indeed lost. But recent developments in M theory and the holographic principle have started changing the picture. The holographic principle is the idea that all information contained within a volume of space, like inside a black hole, can be described by a theory living on the boundary of that region. It's like a hologram, where a three-dimensional image is encoded on a two-dimensional surface. This suggests the information about what falls into a black hole isn't lost. It's encoded on the event horizon and slowly played back to the universe in subtle correlations within the Hawking radiation. The information is scrambled, but not destroyed. Predictability is saved. So where does this leave us? We've journeyed from Einstein's curved spacetime to the quantum fizz of the vacuum, from the beginning of time in a no-boundary nutshell to the mysteries of black holes and possible extra dimensions. We find ourselves in a brand-new world. The latest ideas from M theory suggest our entire four-dimensional universe might be a brain, a membrane floating in a higher dimensional space called the bulk. Matter and forces like electricity would be stuck to our brain, which is why we only perceive three space dimensions. But gravity, being the curvature of space-time itself, could leak out into the extra dimensions. This could explain why gravity is so much weaker than the other forces of nature. Most of its strength is diluted by spreading into the bulk. This isn't just wild speculation. It makes testable predictions. For instance, at very small distances, gravity might behave differently than Newton's law predicts. Experiments are currently underway to test this. In one version of this brain world scenario, there could be another shadow brain parallel to ours. We'd never see it, because light is stuck to each brain. But we'd feel its gravitational pull. The mysterious dark matter, the unseen mass that seems to hold our galaxy together, might just be ordinary matter on a nearby shadow brain. Perhaps the most mind-bending idea of all is holography. If the information of a volume can be encoded on its boundary, could it be that we, who think we live in a three-dimensional world, are actually just holographic projections of information stored on a two-dimensional surface at the edge of the universe? In this view were the shadows on the wall of Plato's cave. Which is real, the brain or the bubble, the world we see or the information on the boundary? From a scientific perspective, the question may not even have meaning. If two models both describe our observations perfectly, you're free to use whichever is more convenient. Reality is in the description, not in the thing being described. From the smallest possible scale to the largest, from the beginning of time to its ultimate fate, Stephen Hawking has taken us on a tour of a universe both awe-inspiring and deeply personal. It's a universe far stranger and more wonderful than we could have imagined, and our journey of understanding it, he believed, has only just begun. The final frontier isn't space, but the human mind in its ever-increasing complexity, as we continue unraveling the secrets of the cosmos. As we reach the end of this journey through the universe in a nutshell, it's worth pausing to reflect on what we've just explored. This isn't just a collection of cool physics facts. It's a testament to the power of human curiosity. Stephen Hawking's greatest gift wasn't just his brilliant mind, but his ability to make the rest of us wonder. He invited us to ask the biggest questions there are. Where did we come from? Why is the universe the way it is? What's our place in all of this? For me, the most powerful message in this book is that the universe is governed by laws, and that we, a species of intelligent life on a small planet orbiting an average star, have the capacity to understand them. Think about that for a second. The universe isn't a chaotic, meaningless void. It operates on principles of profound mathematical beauty and elegance, and we can grasp them. That might be the most astonishing fact of all. Hawking's work, from the no-boundary proposal to black hole studies, constantly pushed against the limits of what we thought was knowable. He refused to accept that any part of the universe was off-limits to science, even its very origin. He showed us that the beginning of the universe didn't require a supernatural cause, but could arise naturally from the laws of physics themselves. This is an idea of incredible power and simplicity. It puts the responsibility for understanding our existence squarely on our own shoulders. The ideas in this book can feel abstract, even overwhelming, but they have a very real impact on how we see ourselves and our world. They teach us humility, showing us the sheer scale of the cosmos and our small place within it. But they also fill us with wonder and empowerment. The same laws governing the collision of galaxies and the birth of stars are at work within us. We are, as Carl Sagan said, star stuff. So how can we take these grand ideas and bring them into our own lives? First, and this is the simplest, take a moment to look up. The next clear night, go outside, away from city lights if you can, and just look at the stars. See them not just as twinkling lights, but as suns, many with their own planets, in a galaxy that's just one of billions. See the light that's traveled for thousands, even millions of years to reach your eyes. Realize you're looking back in time, and that the universe you're seeing is an expanding, evolving, dynamic place. Let the scale of it sink in, its perspective changing. Second, embrace the spirit of inquiry. Hawking's entire life was a testament to the power of asking why. Don't be afraid of complex ideas. Don't be satisfied with simple answers. When you encounter something you don't understand, see it as an invitation to learn. The universe is full of mysteries, and the joy is in the exploration, not just the answers. And third, appreciate the beauty of complexity. The journey from the Big Bang to the present day is a story of increasing complexity, from a hot soup of particles to the formation of atoms, stars, planets, and eventually life. Our own evolution, both biological and intellectual, is a continuation of that cosmic story. We aren't separate from the universe, we're a way for the universe to know itself. Hawking left us with a vision of the future that isn't static, but one of ever-increasing complexity and understanding. It's a future full of challenges, but also limitless potential. As he said, I don't think we will ever stand still. We shall increase in complexity and shall always be the center of an expanding horizon of possibilities. That's his ultimate legacy, a vision of a universe not just to be observed, but to be explored, understood, and cherished. We've journeyed through the cosmos in a nutshell today, touching on some of the most profound ideas in science. But I'll be honest with you. A summary can only ever be a map. It can show you the landscape, but it can't give you the feeling of wind on your face or earth beneath your feet. The real magic happens when you read the book yourself. It's in the quiet moments when one of Hawking's brilliant analogies, or a simple, elegant phrase, clicks into place and rearranges your entire view of the world. This summary is a doorway. If anything we've talked about today has sparked your curiosity or filled you with wonder, I urge you to step through it. Grab a copy of the book, because reading it isn't just about learning. It's an experience that can genuinely change the way you see yourself and your place in this grand, mysterious universe. A link to the book is in the description. Also, if you found this journey valuable, please take a moment to hit that like button and subscribe to the channel. That way, you won't miss our next exploration into another life-changing book from the billionaire's bookshelf. Let's keep learning and keep wondering together.